Hi students, today I am going to discuss the Diffie-Hellman key exchange algorithm. So in the public key cryptography, there are two algorithms are there. One is the RSA algorithm and second one is the Diffie-Hellman key exchange algorithm. These two algorithms are very key role in a public key crypto system. And before I explain this Diffie-Hellman key exchange algorithm, first we need to identify what is a public key crypto system. So in public key crypto system or two key crypto system or asymmetric key crypto system. So these three are the different names, either the public key crypto system or two key crypto system or asymmetric key crypto system. Now what the concept of this public key crypto system is, each end user can generate the pair of keys. The pair of keys are a public key and the private key. So this concept is already discussed in the previous videos, the concept of the public key cryptography. Now I recall some of the important points which are used in the Diffie-Hellman key exchange algorithm. So here each end user can generate the pair of keys. So one is the public key and second one is the private key. So out of these two keys, the secrecy is in private key, not in public key. So both end users can distribute their public keys and they can keep up their private keys. Now coming to the Diffie-Hellman key exchange algorithm. So what is the concept or statement of this Diffie-Hellman key exchange algorithm is, two users can exchange a secret key securely. So that means two users can generate a secret key with the help of the public key and the private key. So here in the public key and the private key, these two keys are interrelated keys. Interrelated keys in the sense one key is related to other key. So here you can observe this particular Diffie-Hellman key exchange algorithm. So how the two users are generated a common secret key. Now we are going to discuss some of the mathematical concept. So what the Diffie-Hellman key exchange algorithm, it is a powers of a depends on the discrete logarithm. What the discrete logarithm is nothing but a powers of an integer modulo n. Using this difficultness of the discrete logarithm, so that concept is implemented in the Diffie-Hellman key exchange algorithm. The powers of an integer modulo n. First, the two out of the two users, so the user A and user B can generate the common secret key with the help of the sum of the notations. In this algorithm, mainly the two public numbers are used. The first public number is the Q and second number is the alpha, where alpha is the primitive root of the prime number Q. That is the relation between the Q and alpha elements. So actually these two are the public elements. That means public elements is nothing but known by the user A and the known by the user B. So that means the two users are used these public elements, that is alpha and Q. So what the relation between the alpha and Q is, so these two are the interrelated and alpha is the primitive root of the prime number Q. So actually these two public numbers are there. And coming to the user A point of view, now you can simply understand this particular concept with the help of this diagram. Now user can select a random integer, that is an XA. XA in the sense suffix XA you can observe here. Here you clearly observe this is an XA. So XA is generated by the user A. That means he select a random integer. Random integer in the sense it is a private. So the private key, that is nothing but a private key XA is generated, is selected by the user A. So actually that value is less than Q. That is the condition of this Diffie-Hellman key exchange. User A can select a random integer XA and which is less than Q, and he compute or he calculated the YA value. So how we can calculate the YA value? With the help of a public known numbers, that is alpha and Q. Here you can observe, this is the second one, YA. He can compute YA, where YA equals to alpha power XA mod Q, where YA equals to alpha power XA alpha power. So you can identify this equation, alpha power XA mod Q. So where YA is a public number and XA is the private number. So he chose the XA and he calculated YA, where YA equals to alpha power XA mod Q. And we know the alpha and Q are the global public elements. Now you can clearly observe this particular equation. So where XA is less than Q and calculated YA equals to alpha power XA mod Q. And coming to this B point of view, user B also select a random integer, that is XB. So XB is a private number which is selected by the user B. So which is also less than Q, and he can calculate it, the user B calculated the YB value, where YB equals to alpha power XA or alpha power XB mod Q. So here the equation you can observe, we can similarly write YB equals to alpha power XA mod Q. So this is the equation. So you clearly understand the XA, sorry, here is the XB. So XB is the selected number by user B, and where alpha and Q are the two public numbers, then you can generate YB equals to alpha power XB mod Q. So now here you can observe both are calculated XB and YB values. XA and XB values are the private numbers, and both are calculated YA and YB values. Here you make it observed XA and XB are the private numbers and YA and YB are the public numbers. So in the public key crypto system, what the concept is, both end user can transmit their public keys, but they keep up their private keys. So now what the public key of the user A, that is user A, YA, and what the public key of the user B, that is YB. So both keys YA and YB are exchanged. Now you can observe the YA of user A can distribute it to YB, the YB of user B can distribute it to YA. So here both are transmitted the values. So that is YA is transmitted to user B, YB is transmitted to user A. That means here you make it understand XA and XB are the private numbers because of they can select their random integer, and based on that they can calculate user A calculated YA equals to alpha power XA mod Q, and user B can select the generate the YB, where YB equals to alpha power XB mod Q. Now you can imagine how they can calculate a common secret key. So that is the important one. Now you can consider a common secret key, that is the K. Now in the user A already receives the public key of the user B, and user B can receive the public key of user A. So now the user A receives the YB from user B, the user B receives a YA from user A. So they can use these two keys. How they can generate the common keys, you can imagine this is the K. The K equals to YB power XA mod Q. You make it absurd here. K equals to YB power XA mod Q. And similarly here the user B also calculated a common key K, that is YB power XA mod Q. Here you can observe the values of this particular key value of user A, how he can generate the common secret key K equals to, he used the receiver's public key, that is YB. So where K equals to YB power XA mod Q. Coming to the B point of view, user B receives so the public key of user A. So he can use that key that is k equals to ya power xb mod q. Here you make it absurd, k equals to, here already yb, here he calculated the, he receives the ya from user b, user a power xb and mod q. So here you can observe, this is a common secret key which are generated by both user. So this is the technique of the Diffie-Hellman key exchange algorithm. Now you can observe some of the merits of this algorithm is nothing but the Diffie-Hellman key exchange algorithm, in that, so user A select a random integer xa, user B select a random integer xb, user A computes a yb value, that is public key value, yb equals to alpha power xa mod q, and similarly the user B calculates the yb, where yb equals to alpha power xb mod q. So here the xa and xb are the private numbers, ya and yb are the public numbers. And the next one is the global public elements. So what the global public elements is nothing but already discussed. The alpha is the primitive root of the prime number q. So that is the relation between the q and alpha. So q is a prime number and alpha is a primitive root of the prime number q. Now user key generation, that means he computes, user A computes ya equals to alpha power xa mod, ya equals to alpha power xa mod q. Similarly the user B generates a key is nothing but, so the public key is nothing but yb equals to alpha power xb mod q. Similarly, they can generate one common secret key where k equals to, the user A can generate the common secret key k equals to yb power xa mod q, and similarly the B can calculate k equals to yb power xa mod q. So these two keys are equal. So this is a main factor in this Diffie-Hellman key exchange algorithm. The two users can exchange their keys securely. How they can generate the common secret key with the combination of the public key and the private key. So they can use the private key and they can calculate the public key. They can send only the public key to the recipient, or receiver can generate his public key and send to the public key to the sender A. So both can be generated, the secret key, that is the k, with the help of the alpha and q. These two are the publicly numbers. So it will fulfill the concept of the public key cryptography, which provides the security of an message to transmit that message with the help of the both keys, that is the public key and private key.